Wow.
Yeah, so you wanna turn off your sound. That way you don't hear yourself.
Yeah.
Good. So if you're gonna present anything, you wanna share your screen here.
From where?
Like she is laughing like so.
No, I don't remember.
Oh, is everything? All right, then maybe we'll get started in just a minute.
Yeah. Like she had my compilation for that price. So now it's like. Yes, we had chicken. Buffalo. She did. She did have things. And then we had. She used to very.
Oh.
Yeah.
That's so that you muted your computer.
Organization of the analysis to just say like, okay, now that you know what we can do.
Right.
Yeah.
Should we maybe step outside and?
Still my dress. No, I'm just.
All right, so Juan? We're going to step outside and discuss briefly, and then we'll come back in and you'll start. your presentation.
Gracias.
No, you can just go to the presentation.
Yeah.
And the PowerPoint, and everything should go away. Just going the presentation. You know, go to the slideshow.
Yeah.
And then
Taking a while, but.
Sorry.
Oh, wait, why is it? Okay. Oh, I think.
You should be able to hide the presenter mode.
Yeah,
from-
switch the screens.
Oh, yeah. Do you wanna come up and? I don't know how to do it on,
None.
yeah. So this microphone should be on, but there's also the speakers, as long as you're addressing the room. People should hear you.
Oh, so like, I should not speak with you.
You can speak through this microphone or, is there a room microphone?
Yeah. No, it's a strong computer. The computer sound is off.
That's, I don't know, that's because you're a computer.
Okay. Now it should work. Okay.
Oh, perfect.
Do you actually use notes? Someone uses notes.
I do, but
Yeah, I also do. Also put bullet points over the computer.
It's so annoying. Hey. Blah, blah. I'm gonna take the mic if it's super noisy. Or maybe here.
be the output for people speaking over so everything's connected to the end room.
Thank you, Mickey. Oh, there is some faces.
Thank you.
Good.
अगर वो
That word,
Can it be just French?
it's a word like they usually use it in English. In like little sandwiches.
Because it's not really an appetizer. You want to use like it's just small bites.
Suggest.
It literally, I think it does translate to like just small bites or finger food.
All right. So, thank you everyone for coming. Juan, take it away. There's a way to. Okay. Oh. Yeah, there's an echo. Yeah, but even if I don't know why it's not. Is your sound turned off?
Yeah. Maybe check the room, maybe the room mic, the room speaker is. Turn off the room speaker.
Hello?
I don't know.
Now? I don't hear it. Oh, but I think it's still here. Well, anyway, let's go continue.
Good.
All right, they say they can hear online, so.
Yeah.
All right, go ahead. Hi, everybody. Uh, my name is Juan Garcia Nila, and I'm gonna talk to you about my thesis defense. Well, my thesis. There's too many things that I did, but I think it basically has three main projects. Because you're already part of my qualifying committee. The last two topics are the things that you may already know. It's just maybe a while, so I just gonna repeat it. But this project, that is the first one, actually involves three papers, so I kind of reduced it, kind of like 5 slides. That is a continuous measurement based holonomic quantum computation for bosonic code. We just put it in an archive like 2 weeks ago, and it's basically extending the theory that Dr. Brun and Arnold worked for GKP codes and CAD codes. And the two papers that I did, that it was part of my thesis too, is first compare continuous error correction under non-Markovian noise, and basically prove that there is an enhancement of error correction due to this noise, kind of like the memory is given to the environment is coming back to the system. And in the third, it's the project that I did with Sihan and Dr. here, that it was kind of an extension from it was an extension from the from Open Quantum Systems class, and we basically benchmark different Markovian and non-Markovian approximations to an exact solution. It was a spin in a bath full of photons at 0 temperature, and we basically established in which regimes this is valid.
I'll fix it.
This is the first project. I didn't add the last QR code. So let's talk about why we're using holonomic quantum computation. First of all, it's geometric and it's robust. You're constantly controlling, like, kind of like this manifold is kind of being deformed into the time. So at the end, you can get a gate, but you have you can do this in an adiabatic fashion, basically like slowly changing what you're measuring. You can get what you want without being leaked out of the space. These presents like an alternative to magic states, but the kind of like the downside is that you require really slow adiabatic evolution. The other idea that we combined into this project was the continuous measurement of stabilizers. Why? Because we can basically do syndrome tracking by basically still continuously measuring the stabilizers. You have information that if you have been leaked out of the code space and somehow to recover back to your original code space. So in this paper, we kind of combine both. We use the holonomic path using projective or it can be also with measurements. We steer the path to correct it back to the original code space. It could be also to the error space, so kind of doing like a polyframing, meaning that you already know what error or what leakage subspace you are, and at the end you basically apply the gate, or you already know what state you are because you have tracked the error. And in order to do that, you have to satisfy the Nila flag error correcting condition. So we are gonna I'm gonna talk a little bit about the theory. Maybe I'm gonna skip some steps because this involves a lot of algebra, but we kind of uniformly rotate the code space, and the goal is to apply a theta rotation and arbitrary unitary rotation at the end of this protocol. We apply this, exponential of I theta h, that is the goal that we want to apply to an initial state. And we do it by measuring stabilizers. There are some conditions that need to be satisfied in order to satisfy the Nila flam conditions. For example, we use a Pauli operator x that is not sigma x, it's just some Pauli operator that, first of all, obviously, exponential of 2 pi I x is equal to the identity because it's a Pauli operator. There is at least one stabilizer in the original code space that anti-commutes with that x, and it has to anti-commute with the logical gate that you want to apply, h. And you can construct an holonomic rotation unitary such that as written like this is like that. At phi at angle equals 0, you recover the identity, but at final at 2 pi, you recover the thing that you want to apply, the exponential of I. And this is the projection at all pi's. How the original code space is being deformed by unitary, where the original code space is just the subspace of all the plus one eigenspace of the stabilizers. So it's a product of I plus gi over 2. And this is the instantaneous code space by applying this unitary gate. And again, when p is equal to 2 pi, you have applied correctly this gate into your original. So let's gonna prove that they actually satisfy the error correction conditions. So for all time t, now I'm just gonna parameterize instead of the angle phi, I'm gonna define phi as omega t, where t is the time and omega is the rotation rate. And you can, like, the equation becomes the one that is above. And you can see that the projector diagram is now time dependent as satisfied the Nila flam condition. You have to satisfy this is equivalent to required, where you have these that we call it errors, are kind of like these errors have been dressed by this unitary, and you have to satisfy the error correction conditions with these time dependent errors. And these are the conditions that have to be satisfied in order for this condition to happen. Yeah.
Are these necessary conditions or are they just sufficient?
I think they're sufficient. They are not. And we are gonna see later when, like, in order to generalize it, we will need to append some ancillas, but you cannot say anything general about the ancillas construction. We get too many months working in a generalization of this, but we couldn't handle it at the end. These are the conditions. The Hamming weight of the x has to be greater than d minus 1. But that means that at least has to be the weight. The stabilizer within Hamming distance d minus 1, d minus 2 in the case of even cases, of x has to anti-commute with x. And the logical operators within Hamming distance of x commute with x, but anti-commute with h. It's kind of too complicated. Just say what are the examples? Which code satisfies this? The generated codes. Why? Because the generated codes have more syndromes than errors. Kind of like you have way a difference with the perfect code that one syndrome detects one individual error. In the case of the generated codes, you have so many syndromes that maybe they don't only belong to one error. There are several errors that can be detected. And how we fix it? Well, we add ancillas. This is a picture of what is happening here. So you have, this is called the Stiefel manifold. Sorry, the space around here is called Stiefel manifold. This is the Gauss-Mannion manifold. I'm not going to explain in detail what it is, but kind of you see the picture. Like if there is, you start with the initial code space, you are being deformed by the unitary to another projector. But if an error has happened, you have two chances. One of them, they correct the path to get to the original code space, or the other one is just keep track of that error that happened, keep evolving it with that error, and you will end up in an error subspace, but you know exactly what error has happened. So you can, at the end of your protocol, know exactly which state you are and get it back. Of course, this becomes way more complicated if you have more than one error. This is only assuming that the chances of having one error in this protocol are low enough that to have it more errors, you can generalize this to many, many errors, but still, it becomes way more complicated. But in principle, it works. So this is like what happens if you want, if, for example, for the 713 code that basically is not the generic code, you can add one ancilla to your an extra degree of freedom to the original code space, and you can also generalize like the edge that you want to apply to append identity, and you kind of like put an X. This is really sigma X onto the ancilla in order to this anti-commit this code space, well, with the stabilizer of this code space, and then follow the same recipe that I have talked to you. You kind of like degenerating the code. You have to go case by case. We couldn't generalize it for any arbitrary. And I'm gonna talk about like this last project that I did, and it was applying this to something that is useful for the industry. I'm not gonna go through all the theory of CAD codes, but it's basically encoding the qubit in this CAD subspace. Basically, the CAD subspace, the 4-component CAD subspace, have kind of like 4 different states, and you take the even states to be your qubit subspace. So the 0 becomes to the 0 CAD, and the 1 logically is the 2 CAD, and your errors are gonna be the CAD1 and CAD3. These are the common logical operators that you use in defining this CAD code using the paper of Ms. Rami. The number operator is just A dagger A, and the quarter rotation, that is going to be the CL, is just an exponential of pi halves of that n, and the parity operator is the square of that. So this will kind of act as your stabilizer. By measuring that, you will see if you are in parity 0 and 1, basically even parity, or if it's -1, you know that you have been leaked out. So this is the error that you can have. Basically, this A, that is the annihilation operator, transforms your K CAD state into the K -1. So it transforms the 2 into 1, or the 3 into 2, and so on. We can define the squeezing operator in terms of a square, and with that squeezing operator, you can define the B of t, that is the rotating unitary that I defined previously. So all of that generalizes with specifically these parameters that were constructed in order to apply the correct gate. And we can guarantee that at 0 you recover the identity, and at final time you recover your arbitrary rotation that you want.
So what is the thing that you're measuring continuously in this case?
In this case, would be kind of like the stabilizer, the P or the generation of P.
So experimentally, how would you, I mean, I realize it may be challenging, but how would one in principle measure the rotated stabilizer?
In particular, like you can have control on these parameters. That's my assumption. It's not that easy. So this one depends on the intensity of the laser and so on. This one will be like I require it to be like this one, but all of this are dependent, by the way. I'm assuming a really big assumption for all of this view. So I'm constantly kind of using it. I don't know if it's a normal line measurement of this P of t. P of t is just like multiplying B of t and P of t dagger from left and right from this operator, just to detect that I've been leaked out of the code space, and kind of like following the same recipe from before. We can just arbitrarily know that an error had happened and correct it right away, or just leak it out, being in the leakage error, and at the end you know that you are in the correct state times the Pauli error that you have. Well, in this case, it's going to be kind of a displacement error. Okay. And this plot is kind of like the fidelity for the plus state, that is the eigenstate of x. And you see how it's increasing until you get at the final time, you get the fidelity one. You are in you're in the correct okay, that is in here I put it for this is 5 points, so it's a T gauge. So it's the final state is T applied to the plus state. That is a non another famous bosonic code is the GKP code. So the GKP code is a little bit more complicated because now, but it's also really more interesting because first of all, it's a stabilizer code. All of the theory of stabilizers holds, so it's much more similar to the original protocol compared to the CAT code that it was not really stabilizer code. You mimic it, but not really. In this case, you encode all the even levels of the harmonic oscillator as 0 and all the odd levels to the 1 logical. Okay, so in the theory of decay bits codes, you can define the displacement operator in terms of these Q and P that are basically different. They have the same shape, A minus A dagger, but the parameters here are different. P depends on alpha and Q depends on beta. They usually call position and momentum, because historically that's how you call these conjugated variables in harmonic oscillator. And in order to satisfy the anti-commutation of these two operators, you require this condition for beta and alpha parameters. Since you have arbitrary numbers here, they define different kind of structures. You can have the square lattice, the hexagon lattice, and so on. In particular, here is the hexagon lattice, where beta and alpha has the same absolute value. One of them is the conjugate of the other. So you can define the X logical and the C logical as just discriminant operators depending on alpha and beta, but since beta is related to Q, so this is just going to be exponential of I square root of Q, and the X is going to be related to it. The square of those ones, XL squared and CL squared, becomes the famous stabilizers. And those are the ones who measure here in order to detect if an error has happened. For the GKP codes, what the errors that you can have are a family of displacement errors. Okay, so basically like the alpha is not really alpha, it's alpha plus some number. This is historically the GKP code used in the original paper of Gottesman, Nila, and Praskill. Oh, sorry, Kitai.
Yeah.
And
Yeah, I've done that.
then I failed. No way.
Yeah.
So it's basically a cubic phase. It's a function that has this cubic. So because it's cubic, you already kind of like destroyed the Gaussianity of this. It's not really something that you can express as a quadratic polynomial. Why is a non-Clifford? They call it a non-symplectic game. But using the same definition, I define the rotating unitary as this. Where f of q is this function is a cubic phase, and this is gonna be my generalization of my x error. This one is the one that is gonna make it rotate the whole code space with these parameters. Kappa is 2 pi t over tf, and g of t. This can be plus or minus. It doesn't have to be minus because it's only like a phase times the state. So phases won't modify the initial state. Or
Sorry. What's GMT here? Is it's in this?
Yeah.
Okay.
It's
Right.
is the amplitude of this p. Is it easy to implement? Not really. I don't know if it's easy to implement. You are assuming that you can have that. So I put it in the paper that in principle you can do it by something called snap gates. At least in the CAT code. I don't know if because the snap gates is basically to modulate like the amplitudes for different levels of the harmonic oscillator. I talked to my friend Cody. You may know him. He's I don't remember who he working with, but but he told me that in principle you can do it. I don't know. And again, at final time you recover the P gate that defined by the GKP. Again, I'm using the definition of that. And this is really similar to the previous one. This doesn't have oscillations, but it applies the T gate to the plus state, that is the eigenstate of X. And this is how it's defined. You initially start with the plus state, and then it kind of reforms into something that it doesn't have too much symmetry. This is the base space. So that's basically it for that paper. Before continuing, I want maybe some questions.
So you've given these holonomic constructions of these bosonic, the CAT codes and the GKP codes, but so what again is the point of doing the holonomic version here?
Well, it's basically kind of like applying the gate, but doing in a not really full term, but like in an error correcting way to correct if an error has happened, if you have been leaked out of the code space, and then apply the correction mid-fly.
Let me rephrase. So why is this strategy better than a straightforward implementation of the same?
Because if you apply like this one, the T gate, the cubic phase, you can have a error and you don't even know that you are not in the corrected state. In this one, by slowly measuring the stabilizers, you exactly know to which leakage state you are. So you can identify what error has happened.
But there are fault-tolerant versions of CAT codes and GKP codes, which are non-holonomic, right?
Yeah.
So why is your method better than standard fault-tolerant?
Well, we need to compare my state distillation, all of these techniques, which I do it in paper. But the cool thing about this one is that you're constantly measuring the stabilizers. We are assuming that that's not difficult. So you can exactly know what error has happened at some finite time t.
And why is that better than just knowing what happened at the end, as is done in the standard programs? Why should I know continuously what's happening? Why is that a better strategy?
To be fair, I don't know. I'm not really familiar with what other strategies there are for these bosonic codes to apply these non-Clifford gates. But yeah.
It's really a general question. Why should we pursue this continuous time type strategy, in particular the holonomic version?
Or like a way, like, well, the original holonomic, because there is like this paper of Victor B. Albert. We're not really criticizing it, but basically the way to do it holonomically is that even if in the adiabatic approximation, you can get leak out, and it's no way to know if you have leakage state or not. This one in particular, at the time that error has happened, you know exactly what error happened. And in principle, you can correct it. I'm more satisfied with, I don't know, a better answer for that. I really cannot come up.
Well, what other effects are there of the fact that you're doing continuous measurements?
Well, you can suppress non-Markovian noise too.
So that would be another factor.
Because you're also being always in the signal subspace. You're strengthening that.
Okay.
I have an easier question for you. Do you have headphones that hook up to that computer? It'll stop the sound. Headphones, just plug in headphones.
Just go to the Zoom and listen. We'll have to stop sharing in the microphone.
Keep on.
Yeah.
Right.
Would the
I think like the Achilles heel of this protocol is how you're gonna come up with a squeezing operator that is independent. You are always driving this parameters. So like why you like that? No, you fix it previously.
In the presenter view. Okay. Did you want to pursue that question or?
No, let's move on.
Okay. So I'm gonna talk about things that I have done previously that you may already know know from the qualifying exam, but this one was a long time ago, so I don't know how much I can recall even me. So yeah, this was a project that I did with Dr. Tucker. It started like a really interesting review of what Ognian did, and then it became like a more generalized version of his paper. So we're basically like the whole idea of this project is to show that the non-Markovian behavior, noise, because it kind of like steals some part of information and it kind of leak it back to the system, then we can use this information leak out coming back from the environment to have an enhancement of error correction. We basically show this by taking a Taylor series, show that the scaling is not as bad as the Markovian counterpart. So let's start with the easiest case, the grid flip correction for 1 qubit. This is more like kind of like a stabilization thing, because you have your qubit, you have your two-level system, you have the ground state, you have your excited state, and you want to avoid to go to the excited state. In the block sphere, the north pole is the 0 state, the south pole is the 1 state, so you kind of want to always drive your system toward the north. So a master equation that describes this one in the Markovian case, it's kind of like this one. You have an error that is sigma x that is constantly bit flipping the ground state to the excited state. So 0 becomes 1, 1 becomes 0. And this gamma, that is this term that describes this operation, this CPTP map. Kind of like if was 0, then you do nothing, you go back to 0. But if you measure, you get 1, then you correct the back to 0. So it's constantly driving the 0 state. You can do this by using measurements. For example, like the idea of Ognian and later from Anirudh, it was to measure x, and if you are in a plus state, you do a rotation with y to the right, and if you measure and you get minus, you do a rotation to the left with y. Or you can also do like the usual case. You measure, you get 0, like the eigenstate. You measure C and you get the eigenstate 0, then you do nothing, you apply 0. The correction is 0. But if you measure C and you get the eigenstate 1, then you apply X to go back to 0. So it's kind of like a general format for describing the error correction. If you are like, this one is really easy, it's like a undergrad level type of homework. If you assume an initial state of the qubit, writing like as a linear combination of all the Pauli bases, then the solution from the equation number 1, it's a time t becomes this thing that looks maybe a little bit horrible, but the good thing, the easiest thing is to see the limits. When gamma, that is like this coefficient related to the to the bit flip is the error rate. So gamma being strong or gamma being much greater than eta means that the error kind of wins. And eta being the correcting rate, so eta being much greater than gamma, then you want to get to the north pole, to the zero state. And that's what's happening here. So the error wins, then you get 1/2 of identity. That means that you go to the center of this block sphere, meaning that you have all the information that you have initially has completely been erased. You have 1/2 of probability of being in one state, but 1/2 of probability of being in the orthogonal state. So you don't have anything there. And however, if the error correction rate is really strong, then you recover the zero state. That is what you want. You can generalize this for a more complicated model. I mean, the complicated is just like another model of, but this one has a non-Markovian behavior. This was based on Sheng-Shi Pan. It was a postdoc with Dr. Brun a couple years ago. And basically you have the Liouville term, you have like the interaction Hamiltonian. So kind of like you have now a 2-qubit system, one of them describing the system, one of them describing the path. It's a really toy model to describe open system dynamics. And they interact with each other with an XX coupling. So X on the system, X on the path, and alpha is kind of like the strength of this interaction. You have a cooling path part, like a kappa B on sigma minus B. This is a cooling process because the description, the Lambda description of this path is taking the excited state 1 to 0. So kind of like this kappa will make the system a little bit more Markovian in the sense that you are cooling the process down, so the interaction with the environment is kind of raised. I mean, if kappa is really strong. And eta is your term that is related to the correction. Exactly the same model. And therefore, we can compare these two models, like the one that I presented previously, that it was the Markovian case, and the decay of the fidelity. The fidelity is just like the projection onto the zero state. The decay of the fidelity goes kind of an exponential. At short times goes linearly. So the solution is exponential, but at short times you can expand this entire series and you decay almost linearly. But for the path coupling, this non-Markovian model, because of sin effect, you have like this quadratic behavior at short times. So it decays an extra order in time compared to the Markovian counterpart. And this is kind of like our proof that the non-Markovian behavior has a better scaling compared to the steep decay of the Markovian case. So now the problem about that is solving that or generalizing that for arbitrary noise. It's impossible, and you have to simulate a lot of things. So the easiest other case that you can model non-Markovian behavior is using an equation that here is the creator of that equation, that is the post-Markovian master equation, that it kind of like involves in an equation that only acts on the system, the information that was leaked out to the environment by this integral differential equation. As you can see from that horrible differential equation, when kappa t becomes a delta, then basically the integral it becomes just evaluated in that at zero time, and you recover the Markovian case. It was the first equation that I presented slide for this project. And if kappa t is not zero or is not delta, then it becomes like a really integral differential equation. But the cool thing about this equation is that it can be solved using Laplace transformation. The usual case or the usual analytical cases are, well, first of all, like kappa t has to be, it has to be something physical. So at zero time it has to be really strong, but when the time passes, it has to decay. It has to be a function that decays in time. It's a distribution function, of course. So integrated over all time has to give you 1, but it will decay as a function of time. So the easiest cases that you can imagine, it's, well, an exponential. And an exponential times maybe some oscillations. These are just like some formats. But why we use that? Because those one makes this problem solved analytical. So all this paper has analytical results for the 1 qubit cases. And we show in this paper that if you have exponential decay kernel with amplitude A and decay factor C, it decays as A squared T squared, similar to the XX coupling, that it was a non-Markovian coupling, that is an enhancement to the linear decay of the Markovian counterpart.
Is this, why does C not appear in fidelity, or is that
It
just
appears
that
up to
looks-
like second order.
Second.
But it does appear. But also, like in this particular case, I think I took A and C. It appears in second order. The case of the overdamped is a little bit more complicated. It's also in the paper, but that in order to solve that, you have to solve a cubic polynomial. In the case of exponential decay, it's a quadratic polynomial. So the solutions are way easier. And so now I'm going to talk about how you can generalize this theory for codes that are in physical qubits. So kind of like it was, I talked to Dr. Juan about it, and he told me like, this is kind of the general recipe. So what is going to be the decoding map? Well, you have your row, that is your state. You basically apply the syndrome projectors to detect what error has happened. Once you know what error has happened, then you apply the correcting unitaries. And then you do encoded unitaries map to the k physical qubits to the n physical qubits. And you finally trace out all these n minus k ancillary qubits. That will give you the CPTP map. And the correcting unitary, that is just the CPTP map minus rho. Okay, let's see an example. This one, it's too abstract. Well, the 3-qubit code. You have two stabilizers. The 3-qubit code basically detects if an error has happened in the 3 qubits by the majority vote. If you have 1, 0, 0, it's highly probable that it was your 0, 0 state. But if you have 1, 1, 0, it's highly probable that it was 1, 1, 1 instead of being 0, 0, 0. So you take the majority. And you're taking out that the probability of having 3 errors goes as p to the q. So if p is really small, cubic of that probability is way more, way less probable. In the continuous version, that probability is gamma d. So it depends on the gamma, that is the error rate, but also depends on your dt time. Okay, so in the 3-qubit code, you basically detect if an error has happened. So you apply these projectors. This basically has no error, or the error was identity. This was an error that this was x1. It's applying to this p0, x1, and x1 from the left and the right. P2 is having an error in the second qubit, and P3 is having an error in the 3 qubit. Now that you detect in which error subspace you are, you can apply the correcting unitary. If you have 1, 0, 0, you go back to the 0, 0, 0. Or for example, if you want in 1, 1, 0, you go back to the 1. And this is encoded unitary. It's kind of like how you, this one that it was just 1 qubit, how you kind of, I don't like to say copy, but like how you replicate this information into your 2 ancillas. This is the encoded unitary that does this. And now you put all these ingredients into that recipe, into that equation, and you get the CP that you want. So that's how you do it. And therefore, in here, I put like a row in the chain diagram for the Markovian 3-qubit case. So now I'm gonna write like the state as a linear combination of 4 subdensity matrix. One of them has no error and has coefficient Q0. Row 1 is average combination of having 1 error in one of the qubits. Row 2 is having 2 errors, and row 3 is having 3 errors. So all of them has the respective coefficients Q0, Q1, Q2, and Q3, where the subindex indicates how many errors you have. So in these chain diagrams, you can see in black arrows, like the jumping probability between these coefficients, and in red ones is the error correction, what the error correction map is doing. And in the case where eta is really big compared to gamma, where gamma is, so the error generator here is a sum of all the bit flip invariants for one of these qubits, 1, 2, and 3. And if the error correction rate is much greater than gamma, then you have 1/2 probability of being your initial state and 1/2 probability of being in the x1, x2, x3 errors. Why? Because this is an uncorrectable error. Once you have the 1, like you were really unlucky and you end up in 1, 1, 1, you're already in the, it's a ghost state. You are already in that error. So that one is not corrected by your methods. So you have 1/2 probability of being in the uncorrectable errors. And but again, we compare the Markovian case with the post-Markovian equation of this model, do it as analytical as possible. And I think we could take an analytical route for this one. I mean, Mathematica helped me a lot. This was even before ChatGPT, so Mathematica still was really, really useful. So the Markovian case is not really, is not exponential. This one has like a decay of gamma t squared. Because actually, like in the classical codes, the probability of decaying here goes like the 1 plus x to the cube. So the first term is 1 minus 3p squared, where p is gamma t. So the first term is something that is squared time for the Markovian case. But the poor Markovian master equation, I was really surprised that it goes as an extra order in time, dq. And this one depends on C, where C is that. In here, I definitely put both the amplitude and the decay rate as equal in order to give me like an analytical solution.
So this long time limit, of course, this is because codes, eventually your luck runs out and some uncorrectable error happens. So the code will not protect you forever. But do you expect the lifetime over which the information is protected, sort of the average amount of time before an uncorrectable error,
Well, it's a
to be longer in the non-Markovian case than in the Markovian?
It's a really good question that I think I never explored. But it would be
We may have talked about, I don't know if we ever calculated that explicitly, but
I mean, here I will need to actually take like the timeline of like the time of decay of this path of this path kernel, like what is the time until like the kernel basically decays 1 over epsilon, and to see if in that timeline what is the probability of being in a correctable state. It would be a really cool question. But yeah, as you mentioned, like here where in the long time, in infinite time, uncorrectable errors happen and will accumulate. You have one half probability of that. But here where I'm kind of saying like even in that case, you are still in the code space, right?
that's true.
That is like I'm defining kind of like this fidelity of being still in the code space, maybe not in the correct, in the initial state, but you are back.
Yeah, well, so clearly if you're correcting very strongly, then it does keep you confined in the code space. But of course, that can include the case you have here where it's an undetectable error, which would also leave you in code space. But there would be some change in the sort of useful lifetime of the qubit that you're encoding. Yeah, I guess we didn't calculate that for this paper.
I mean,
so anyway, yeah. Oh well, maybe someday.
I mean, again, this one is a really simple model too, so we can explicitly know what this timeline, because it's kind of like how much the kernel, the memory kernel has decayed. You know.
On the Markovian side, it's a little bit concave down at the start.
Yeah.
And I associate Markovian behavior with like pure exponential, like always concave up. Am I missing something here?
Oh, this one is because the 3-qubit code has this behavior. Like the probability of
it's just
error
because
is 1 minus 3p squared.
Right.
Is
Yeah.
like the probability is 1 minus p to the cube, but only taking the first term in
Like individually exponential, but then you also have correction. Got it.
What role does the error correcting generator play in your analysis? You actually calculate it?
Yeah, well, in this case, to the order. I mean, it's more like the error itself, like the non-Markovian error is helping to the fidelity scale better.
Error correcting generator at the top of the slide.
Yeah.
Right, yeah, so you wrote it down, but I'm just curious, you actually calculated anywhere in order to obtain the expressions that you listened to here?
I think you could do it by until like the next order.
Well, he's just talking about phi of rho minus rho. Do you actually evaluate the PMME with an explicit expression for that?
Okay, and so when you know that generator, so,
I think I have it in here.
I put it in here. Yeah, it's the exponential of it's in here.
So where is it in there?
So it has in two parts. First of all, you have in here the individual term, but you have also this error term.
So which is the term that involves that phi?
This one and this one, the one that has gamma.
Okay. You have the expression for gamma? I believe you did show it.
In this case, it's here. It's gamma of rho is phi rho minus rho, where this CPTB map in the case of the cubic code.
okay, I see that, so on the previous slide, so how does it actually help you with your calculation?
In here?
No, go back one more,
Here?
so you pointed at the PMME there.
Yeah. So you have, so this gamma dx is the noise. When kappa t is delta, you recover the error correction plus this one for the error. But if kappa t is not zero, is not delta, then you have this contribution and this contribution. So kind of like the error correction is helping you here when you integrate, but you also is helping you here.
So, okay, so you're saying that this PMME actually includes the error correcting generator explicitly, and this is how you're calculating your fidelity. Okay, I still don't see how the error correcting generator shows up there, but you said kappa t and I didn't see kappa.
Oh, kappa is my memory kernel, but the gamma is the one that is the error correcting map.
Yeah, okay, that's that first one with the
The
data
first
in
one
front of it.
and
Okay.
also in here.
Yeah,
You have
it's
to
unclear,
include it
there's a
also.
capital gamma and a. I think it means the capital gamma. So,
Yeah, the capital gamma is the error correcting map.
Good, thanks.
So well, now the fun one, but this is more like to show off rather than actually telling something new. But well, it kind of tells something new. First of all, the 5-qubit code. This is a perfect code that allows you to correct all the types of all the 3 types of errors, the poly errors X, Y, and Z on one of the 5 qubits. So the error channel is the depolarizing channel. And so this is how you have it, the sum of I to the 1 to the 5 of X, Y's, and Z's. And this is the Markov chain. It's a little bit more beautiful. The blue arrows are going to be the error arrows. And all the possible states that you can go through these Markov chains are listed here. So you start with the 0. It's having 0. The number means how many errors you have and what type of errors you have. Example 0 means that all of them are identity, but 3A, 3B, 3C means that you have all of the same type, one of different type to the other 2, and this one the 3 of them. In color yellow here are represented the code stabilizers. Any state times that code stabilizer will still be state, so it's already in the code space. And in the green, they are also in the code space, but this one corresponds to the uncorrectable errors. You have these uncorrectable errors that are usually the ones written in the 5-qubit code, but these times the stabilizers will give you this class and this class. So it kind of like all of these are versions of the logical errors, just dressed by the stabilizer. And the stabilizer, so similar behavior in the limit when rho, in the limit of the state when eta and t's are really, really big, then you recover this state. That is actually the maximal limit state, but it doesn't seem here. That is the maximal limit state because of these coefficients. But if you divide the rho 3b by 1/30/180, you recover like all of these states have the same probability of being chosen. This is the maximal limit state. Sorry, not the maximum. Sorry, is the kind of it's the maximum limit state, but in the correctable set. On the
You mean in the code space?
yeah, in the code space. Yeah. So all of these are in the code space. All of them. The error is really big. You can also the error correction rate is really big. You can also do the gamma really big, that is the error really big, and you get all of them has the same probability of being. Just, in other words, that is the maximal limit state. Sorry for my word. And these attractor points are gonna be so all of the red lines represent like the corrector the jumps made by this error correction procedure, and all of these are points in the code space. It could be a logical error, it could be stabilizer, or it could be just identities. Okay. And similarly, the same plots, but now for this case, this one cannot be not anymore. Well, you can expand it still in cellular theories because you can put the matrix form, expand it in the matrix form formulation, and you still can get explicit expressions. But the exact analytical equations for this one is impossible, so you need to do it numerically. But it's kind of the same behavior. The Markovian case, again, it's the case like quadratic in time, short times, but the post-Markovian equation, the case one extra order in time. So you have the same behavior that you see in the 3-qubit case in the 1-qubit case. Here I'm plotting for different error rates, of course, like higher the error rate, for different correction rates, higher the correction rate, the red one, for example, is closer to 1.
So this extra order, this is the suppression of non-Markovian errors?
Yeah. And you can generalize this one. I mean, to generalize for any arbitrary codes and so on, complicated because you need to have like a general theory of that. But that is the goal of this paper. And before going to the last project, I want to see if there are any questions.
So what should we take away from this? That it's better to do error correction in the presence of a non-Markovian environment?
You know, like whatever it was stolen by the environment, somehow you are able to correct it. The way to do it is maybe the thing that it could be another project. You actually can get back all the information. We have done something similar by the self-information annual is also working a little bit that. Like you are doing continuous measurement while the protocol is running, and you can integrate the measurement current and see what is the syndrome, and therefore. There's also another paper, Pets Recovery by the this was. Watching his name. That's kind of the similar flavor.
They're doing a kind of continuous pets recovery map. Anyway, if you can do it, it's definitely technically challenging.
But this is basically just seeing like the signal effect is helping us. Theoretical paper. Not really much technical paper. So I'm gonna finally talk about the last project that is actually my first project that I did during the PhD. This was when I was still kind of a master's student. I mean, I was a PhD student, but I was taking the classes. And this is how like my inspiration for non-Markovian behavior started. It was a work that I was doing with Sija, that is in the back. We were like a summer trying to do it, and it was really cool. It was one of my best stories here in PhD because we have like 3 weeks or less than that to finish it, and we were able to as much as analytical as possible, and it was really cool to finally have a paper on that one that was published in Physical Review of Lab. It's a really good journal. So
the message is we should always give you 3-week projects.
yeah, I mean, I think that That was a really fun project, and I've seen other students when I was TA of optical system that they have been really, really good, and they have published really good results. I don't know if they're still the thing. Maybe with ChatGPT it's a little bit easier, but I don't. Yeah, this was pre-ChatGPT, so I'm not saying that more merit, but still, I would like to say more. So, okay, so let's gonna go to a solvable example, because the goal of this paper is to compare with the exact solution of a problem with some usual non-Markovian and Markovian equations. The goal of this project is kind of saying like in which regimes each of these is valid, in which one is not. And kind of like it's pretty logical that having strong coupling, you will need more non-Markovian equations, but having really weak coupling limit, you can just use the rotating wave approximation of the usual Markovian equations to describe. So let's assume that you have zero temperature. You have a leaky cavity, meaning that you have a qubit such that it's being constantly bombarded by external photons, and basically the photons follow like an harmonic oscillator path. But at zero temperature, you are gonna assume that there is only the one excitation problem, meaning that while the qubit can be excited to be in the ground state and the excited state, the path at most can be in the vacuum state, excitations, or in the one excitation problem. One of the modes, or one in the infinite level of the harmonic oscillator, goes this photon, but then it cannot be another jump to another state. That is the assumption that you can it's valid at zero temperature. And it has barely enough energy to be pumped out to one of the excited states, but not enough energy to go even further. This is the general Hamiltonian that has the system part, that this is just like the qubit Hamiltonian. You have the path, this is an harmonic oscillator, and the interaction that we have between both, that is much more complicated than the exact coupling between the system and the path. Previously, this one has, they call it James Cumming. Basically, if the path is excited, the system is de-excited or is going to the ground, and vice versa. If the system is excited, the path just goes down. So I'm going to explain later where this model comes up, but it's a really trivial model. At zero temperature, I can express the joint state solution for this one as this thing. You have coefficients, one related to being in the zero ground state, vacuum state, being in the one excited state, this in the qubit, and the vacuum state, and the coefficient related to being always the system in the ground state, but one excitation, one of the modes. This sum is overall K, so it's infinity sum. And yeah, this the cavity vacuum, and K is basically applying the creation operator in one of these modes of the code.
So if you wanted to use a model like this, where would you get the GK coefficients in the B operator there? GK, where do they come from?
Yeah, that's a pretty good question, and actually it's really the next slide. Yeah, but I think I skipped it. But what we usually like, so you have an infinite modes here. So these ones kind of like are the density of states. Well, so I don't call it density of state, but it's related to like the Fourier transform of JK as JK gives you the spectral density. So it's kind of giving you like what is the amount of energy for that mode K. Right? So what you do is kind of like do a spectroscopy and see how for different values of energy, the amount of levels are filled up. That usually depends on the model. For example, we use the Debye model, or we use, well, in here one, we use the ohmic path because it's the usual one for describing photons. But in principle, you can have a complicated version. Well, in this project, we did 3 models for the spectral density. We did the delta because the delta describes the delta. Oh, I don't know if I put the delta here, but I can. Well, I have here the delta, the one triangular path that is basically like it goes linear in frequency and then it's 0 at some good of frequency. Here, I think I just put the most beautiful one, that is the ohmic path. And the cool thing about this one, I'm just going to focus on the population. that is the probability of being in the excited state. So if you start here, we start in the plus state, so it's the eigenstate of x. So you have 1/2 of probability of being 0, 1/2 probability of being 1. And and then you start in 0.5 population, and then the exact solution that is in blue kind of do these oscillations, these blue oscillations. However, and I'm not gonna describe too much about this equation. Well, if you want me to describe it, I'm gonna describe it, but how you come up. But the time convolution as linear approximation that are truncations of the Nakajima-Swansea operator are gonna be best to model like these oscillations in the exact model. So the DCL4, that is the time convolution is at order 4, matches the best to the exact solution. The yellow one is at second order. That is also the called the Born-Redfield equation, and also has these kind of oscillations. But the Markovian cases that are the cross-graining Markovian equation and the rotating wave approximation. The rotating wave approximation is the usual one where you grab the path correlation function, you integrate instead of from 0 to some time t, you integrate from 0 to infinite. So basically you are integrating all the path. So you are killing all the bad degrees of freedom, and you only kind of like, you have the exponential decay, basically like all the error rate comes from the integral of 0 to infinity. There is the coarse graining one. The coarse graining is gonna be the best Markovian approximation for the model. Is basically optimized with the exact solution. So because we have here the exact solution, we have like an ansatz for a Markovian equation, some parameters that we can be optimized by taking the trace norm with respect to the exact state. So basically we minimize the distance, is the trace one. We minimize the distance between the exact state and the approximation ansatz. And we come up with the best coefficients that match the best. That's what you see. That's what you see in the trace. The coarse grained is closer to 0 than the usual rotating wave approximation. And as you can see, the non-Markovian equation, this error is the minimum. So this one, it was like a really long project just to say, like, of course, if you want a stronger non-coupling, you'll need to consider, or like this behavior or oscillator behavior, you need to consider a non-Markovian. There are some works done by Dr. Davidovic to go even DCL6 and so on. Like they still keep. And it's basically like an expansion of the Nakajima-Swansea.
So the TCL4, the green curve, seems clearly the best approximation to the exact in most, if not all, of these curves. But is that something where it'll drift away if you kept going further?
Depends on the model. For example, the model of this one. This is a horrible one. Like this one is a really strong coupling because you have just a delta on the spectral density, and this one can be sub-analytical. This is I think it's even like in the optical quantum optics by Scully book. They have this problem and they solve it, and the equations are just cosine squared. So the probability of excitation is cosine squared. For this TCL4, because it's a truncation of the Nakajima-Swansea, it of course at some point is truncating the information from the band. So you have this oscillation, it goes up and then goes back. At some point it diverges because it's not capturing all the memory that was leaked out from the system. Yeah, it's not always. Yeah, I mean, at a short time it matches because it's in effect. But when you have more, like in here, the problem is that the decay rate becomes negative. So it's exponential to minus gamma t. If gamma is positive, then it decays. So on that behavior, it's really good. But when you put the other sign, minus times minus gives you plus, it's an excitation. So you can have non-complete positive behavior, and this is basically what's happening. At some point, it diverges, and the probability is no longer one. So in that regime, is not valid. We have an explanation there of why this happens, but basically is that different initial conditions will get you to the same state. So it's not invertible the problem, right? If all like if like A, B, C gives you the point B, then when you go back, B who it came from, A, B, or C. Okay. And yeah, it's this is that's it. Let me see if I well, any other question before I finish this? Yeah, questions about this one?
Where's that beautiful bridge?
Which
The
bridge?
bridge. That
You had
bridge.
the bridge is your background.
I don't know. I think that's like from the stock photos
Oh,
from Windows, but
It's an AI generated bridge.
Don't
I
want to
don't
walk
think it's a
across
quantum
the AI
bridge or
generated.
something. I mean, just the last slide that I don't know why I didn't have it in that presentation, but it's kind of like this one. I mean, it's gonna happen the same. So I'm gonna you said Conquer to stop sharing, and then share it again, right? So you put it here. You have to start present. Yeah. So just
So if you walk across an AI generated bridge, it turns out to get these.
so
Gotta be dreaming.
these are like two architectures that give you that James Cumming Hamilton. Like this is just to justify why like the James Cumming is enough. Which is not actually enough, but both of them have different parameters. Both of them, one of them is a qubit interact with the resonator. The other one is just the experimental circle is a read laser in the trap ion, trap atoms, trap atoms by read laser. And both of them have, this is the general Hamiltonian, and both of them will give you the exact same format. I mean, in here I have more terms than the one that I draw it, but the non-rotating terms I'm just killing it. Sorry, the high rotating terms I just killing it in the rotating wave approximation. So these ones that are 4 terms now just become 2. But both of them comes because of the coupling between the qubit, and here is the Rasmon qubit with the resonator, and in here is the hyperfine levels between the atoms and the induced levels. Both of them. And you can, in principle, these factors that you asked before, Dr. Brown, the G and so on, can be put in terms of the different architecture, hyperfine level, or the parameters of the charge and the capacitance. That's basically. Oh, I don't know why. Not okay. So, let me see if I. Yeah. Well, thank you very much for everything. Before finalizing this, I want to ask you if any of you have any more questions, comments.
So these 3 papers, did you have any other papers that came out of your PhD work?
Yeah, I mean, as I mentioned it previously, like I have in total like 5 papers. The one that I had with you, Dr. Vidar, the continuous measurement bosonic codes generate 3 papers because it was a lot. The first one, it was like the theory that was developed with Dr. Brun. He gave us like a really big set of notes about how to do this protocol. That became self a paper. Then the second paper was more an input of Anirudh, but I also participated. That is the steering paths. Basically, like now that you have the syndrome tracking, now that you know what errors have happened, how you modify the angle or the path in order to take it back to original code, and that itself. And in that paper, we also do a really big analysis of non-Markovian noise. So that is the justification. In particular, he used an stochastic version, like he modeled the non-Markovian noise by putting a Hamiltonian that is stochastic.
What did you do?
Oh, in that paper, yeah, well, analyzing with him that, and in this, and finally, the bosonic code was the idea of me to actually use the continuous measurement based on holonomic protocol to a specific architecture that is the bosonic codes and the GKP codes. The CAD codes. And the GKP.
So you were basically you did the whole thing pretty much. Yeah, in just a few weeks.
Yeah.
So maybe we should only give
Oh.
3 weeks to. Right.
Which, by the way, well, I didn't have it here, but there is, we took a year kind of because we were trying to implement this to the surface code. Dr. Brew was a witness of that, and me and Anil were really hard of going like the surface code. And in the problem of surface code is that in this case you need to measure stabilizers, but in the surface code you have like this high weight operator, right? So we kind of did some trick by using Mila's Marvian's paper that his was basically the pi-4 conjugation. And it was to divide this high order operator into something that it's low weight and measure that. But the problem is that break completely the distance when you do this. So there is no way to save it. We tried so many times. Maybe at some point we tried to go to a no-go theorem, but basically this doesn't hold the same thing. We wanted to do as much fault tolerant as possible, but in that case, once the distance is destroyed, you cannot claim that there are correction conditions. So that's why it took so much time. So maybe because of the trauma of that, we wanted to implement it into into a different code, in particular the bosonic code. It was pretty cool, first because I really am interested on that, but second of all because we claim that even maybe it's not easy. It's quite straightforward to know what you need to do. Generating these squeezing operators and these displacement operators are not something difficult. To actually have control over them, I don't know if they are, but to create them, it's pretty. There are so many techniques. I propose the snap gates, but they are out there have like many.
Yeah, I think in principle you can do it. You have to have control over how you're coupling to your bosonic states. So I don't know if that you can just change the squeezing parameter that you're driving it with as you go along, or anyway that would be a good thing to be able to figure out. But the theory,
I think the answer is
fairly straightforward.
not easily, but all things are possible through thunder.
Also, another idea that was also inspired by Sishin's work, there is what I have seen and so on is like kind of like these code switching techniques. Like some of these codes, for example, for these surface codes, basically, well, maybe not for the surface code, but there are some other codes that you can switch. Like the good thing about code switching is that you use a code to implement some gates, but other gates that are transversal in other codes are not done in the first code. So basically, you switch between code A and code B. If we can do this by using the holonomic, that's an idea that we came up with.
But eventually people want to graduate and go on and like have a life. So,
Some people.
you have to draw the I mean, other people. Anyway, yes.
So that's basically it.
Any other questions?
And basically, like what I want to end up saying is that kind of like humans do mistakes. All of those will do mistakes. Errors will happen always. We saw like if non-Markovian has taught us something, is that first of all to acknowledge that errors happen. First of all, second of all, if we have some kind of trace that an error has happened, and we can some kind of subtract by memory what was done wrong, we can maybe correct it. And using this holonomic protocol, maybe we can start over. Never give up. Yeah. Thank you.
Thank you. If there aren't any other questions, maybe the three of us step out.
Or we can all leave.
That's easier.
There's a lot of you. Plus, there's all of them. Yeah.
Because some of them have avocado. I don't know if I did it good. How many
So the first one was.
I mean, it's only like
Been taking a field trip. Te vamos.
Some of the.
Yeah. How is it? Did you already have your
Yeah.
But it's almost kind of.
And then the second time he
Yeah.
came back, he had
Where are you gonna
18. Oh no, most of them were easy, like.
Well, the open.
Did like have a
Like,
question.
Llegaba casi mira, ¿entendés?
Where is
Llegaba así, pues, ¿dónde se queda?
Easy, but I canceled.
Sí.
Well, on.
This is not related.
Like.
But you can also see like which related papers
But
have like
what I
the
found-
content usually. Journals are kind of weird, so they want you to cite their own paper. So usually it's easier.
Flag, like flag.
That's what happened. Like, I mean, I was presented in the physical review. Like, well, not a lot, but at least two. It's like, okay, they are in the same. But usually, like some of them, like, hey, your work is interesting, but it's far from the scope.
Entirely full.
Like, they usually say, like, we visit the interesting, but it's far from the scope. Or something like maybe the photos are there.
I don't think so.
Right. Or sometimes it's like we have so many missions.
I made a mistake. If you.
But it's usually the best when they actually
¿No se
get it.
entiende?
It's really awful, like for example, what happened to her. It took so much time. It was fun. Did you take him?
I just got it, so.
They were fine.
When did
here.
Last one.
All at
Where do we-
I didn't come to I was online because I was in India.
I didn't know that you were. I know that a lot of people. Yeah. At least you will have houses. Living. Me.
And then there's very few people after you guys.
Very good. Well, I don't think it's very friendly. You. And most and out. I mean, you know that before us, that used to have like three adults. It was at some point it was John. Oh, and that's it.
Like the reviewers we have.
That's why he could afford us. Dr. Garcia. Oh, congratulations. I thought they were gonna fail me.
Doctor, congratulations.
Yeah. You'll need to. I don't know what website you go to, but you set up the thing for submitting the thesis to the university, and that then contacts the three of us to. So that's separate from the maternity.
It will only cost you another $500. Venmo later.
Another 5 years.
I wish that the money goes to you. It goes to the. It goes to USC.
Yeah. But yeah, so when you're ready to upload that, so we can sign off on it.
I think I already did it.
He's done. Yeah, but there was a bit of a delay for him because I think he didn't realize there was that additional step. So there is that additional step. So if we don't get it, I'll remind you. So you got all my comments on the holonomic thing, so that applies of course to that.
Yeah, and I also submitted. Well, we submitted to MPJ Quantum.
Yeah.
Let's see the luck. If not, maybe we will. Well, maybe we can try again QST.
Yeah, well, let's assume that it will go well.
You realize that all these journals are charging more.
It's ridiculous.
MPJ Quantum is now like 5,000.
It's like $5,000.
The good thing is that I was out for this summer, so I think there's enough funding.
It's a great journal. It is.
The money I would have paid you, I will pay to
$7,000 to
publish
major
this.
communication.
Anyway, congratulations.
Also, well, I didn't mention it here, but I'm working on the adaptive encoding that I mentioned for like the neutral atom stuff.
Yeah.
Maybe we can get together and discuss.
Yeah.
it.
I would be happy to come. This is already getting a start on what you'll do for your.
Yeah. Well, Singapore. Okay. I'm going to Singapore soon. So.
I'm very proud.
Thank you.
And also thank you. His cousin.
His cousin. Congratulations. Your family is all very talented.
I'm very proud.
Anyway,
And thank you for the letter of recommendation with Dr. Angie.
Of course, yeah.
I'm gonna be working with her
It's a great place.
September 5th.
I hope you like humidity though. That's the only thing.
I mean, I prefer it than cold weather.
hot and humid.
Yeah.
And also, yeah, I'm gonna work for neutral atoms now. Sorry. Okay.
Don't you laugh?
Please,
No, I don't know.
have everyone there.
No, I mean it's gonna be error. I mean, like they are not. I'm not gonna be really working on neutral atoms. It's just error correction,
Mhm.
but in particular for erasure. And so on. So they want some. So I told them like right away. I don't know anything about neutral atoms. Just be clear, and they like, yeah, we don't really care too much of that.
Erasure codes where you get to rearrange the.
Fun stuff.
With Pascal. I mean, I tried so hard to get into US. It's not the best.
It's a really good place, and Rikun is a very good.
I mean, I knew
He'll
could
do-
get the job at Seagull Tree, but he was also really battling
Yeah,
to
there
get
was
the
a-
job.
There was a lengthy period where
He didn't even get like interviews and so
it
on.
seemed like there was a long drought, and then he got, I think, a bunch of interviews after he'd already, there was a long period of nothing, and he got a bunch of interviews.
He's really happy. He will. I think it's. I don't really know what the company does. I don't. I also he hasn't started, so he's like applying again like AI.
If you want to
quantum.
stay in academia, then you're doing the right thing.
Yeah, I really want to. I mean, I really enjoy to be PA, as you all know. I really like to interact with the students. That's my main. I mean, sometimes maybe I shouldn't say it, but sometimes I enjoy it more than research. But it's part of the same thing. I mean, doing research is also
Don't
teaching.
say that when you're, but yeah, no, this is the way to go if you want to do that. The postdoc like this. When you're a postdoc, that's when you can really concentrate on doing research and have no other responsibility.
Yeah,
You
you
should
have
make
funding
fun.
responsibility.
That funding is not your problem. It's
And
whoever-
Singapore is a very wealthy place. They don't have funding issues.
They've got funding, and a lot of people from Europe go through there.
They're gonna pay me 7. It's pretty good. I was like, maybe I was called by the money. Anyway, thank you, doctors.
It's a good place to come.
I hope that you like the plans. It was done by a
Oh, yeah.
friend of me.
Yeah.
It was delicious.
He was someone like
And I really
Lisa.
appreciate you also bringing something savory. All we ever get in these things is sweet stuff.
Yeah.
That was great.
Yeah, Pigeon is. I don't know if you have gone to Pigeon. It's a really good place. It's in downtown, in front of Pershing Square.
Noted.
So, congratulations. If you want to chat about anything,
Maybe.
still.
I'm not sure if I'm gonna come on Thursday. I think there's something to you. But yeah.
All right.
No worries either way.
Congratulations again.
Congratulations.
Thank you, Dr. Eli. Thank you, Doctor.
Thank you.
Great.
I
Glad to see you go.
I
I'm very
spoke to Dr. Sanari, but he couldn't. I mean, he didn't. That's why.
Yeah.
I mean, he maybe would be interested on the holonomic part, but he already knows what we did. So yeah.
All right.
I'm also gonna send these maybe to Dr.
Oh, yeah. Yeah,
Because
you
he
definitely
will
should,
work
because he
in-
was really interested in.
I mean, he was interested on the GKP stuff. And
Yeah.
This one is kind of a.
Well, he may wanna, if we, I don't know if we'll have time, but if there's a follow-up on this, he might be interested in working on how would we actually engineer the system. to do
I know that Andy and Dr. Grover were.
Yeah.
And since Daniel is already having like this connection with them. Okay. All right. Thank you, Doctor. See you.
I'm very happy that.
Thank you. Thank you everyone for joining. I'm gonna
Letting
end
him go, but happy for him.
Bye. Thank you.
Thanks.
Yeah, and we have a picture, I think.
Oh, yes, picture.
You sent it to me.
Picture didn't happen.
Maybe you want to put your slide back on? One?
Onkar, can you take? I think it's better to say like all the people that were.
Yeah, it's a lot.
Thank you, Dr. Ren. Thank you.
Thank
For
you for
coming.
everything.
Yeah.
All right.
Goodbye, everyone.
Take care.
Thank you.
When you're leaving, guys,
Yeah.
Yep.
Sure, I will make it.
Oh, you're doing this, you wait.
Yeah, I mean, in theory, I need 60 days to abandon that.
Oh, yeah.
There is like, if not there, like.
No.
Until my attorney finishes.
Just get it out there.
But also like, I don't know if,
I would say that. No, but yours is supposed to start.